Good.
Okay. Who is absent today? Aha. Who wants to grow? Okay, it's excellent. Today's topic is IMPORER integrals. IMPORER integrals. In Greek, Hosmas integralar. In the lesson, we learn about the IMPORER integrals type. Because IMPORER integrals separate two groups, first type and second type. First type of integrals called limit infinities, and look like this: negative infinity to positive infinity, f of x, differential of x. And next we should learn about solve these example problems. And second type, there is not limits is not infinity. Limits bounded a to b, but under the integral function unbounded f of x dx. There is a f of x is unbounded. That's why it's between the minus infinity to and plus infinity. And next we learn about its properties. And first property is if f of x greater than g of x, there is also literal integrals of these functions look like these proportions. That's why we can write this function, this integral. And this property also used for first type and second type of integrals. And okay, there we see example of first type of integral. First example: 0 upper lower limit of 0 to upper limit of infinity 1 over the x squared dx. And look like this definite integral. It is equal to 1x over x, but we should write minus sign because the differential of derivative of 1 over x is equal to minus 1 over x squared. That's why we write minus. And we use 0 and plus infinity. Also next we can use Leibniz formula. We all know Leibniz 1 plus infinity is equal to, and it is not, there is not x could be 0. That's why this integral is not defined. Isn't defined. It is if there is a lower limit equals to 1, this integral we can evaluate this integral such as this. It's not 0, it's 1, and there is we use 1. And from the Leibniz formula, minus plus 1 over the 1. And we all know 1 divided by plus infinity, it is equal to 0. It's equal to 0. And 1 divided by 1, it's equal to 1. And we can solve this problem so it's equal to 1. Okay, it's called limit of this integral function, and it is look like this. We can write minus infinity to plus infinity f of x is equal to limit function, but we replace infinity with t, and we can take the integral minus t to plus this. This is the definition of this IMPORER integrals. IMPORER integrals with limit of this formula, and we can separate this integral into two integrals: minus infinity plus infinity f of x is equal to both sum of both integrals. It's minus infinity to 0 f of x dx, and the next 0 to plus infinity f of x dx. And we call is additional properties of these IMPORER integrals. These properties commonly used evaluate this integral, and we show us some examples for this formula. Example 2. 1, 2 plus infinity ln x divided by x dx. We should evaluate this integral, and it's equal to 1 plus infinity ln x. We all know 1 divided by x is antiderivative of ln x. That's why we can write the ln x. The ln x. And we can replace ln x with t, and this integral is equal to t dt. But we should limit look like this, because it is change. That's why just we use this integral, and the result is dependent to t. And we all know this is equal to t squared over the 2, and we replace t with ln x, and the result ln squared x divided by 2, and the limits 1 to plus infinity. Also, we all know ln squared infinity is equal to infinity, because if x is gross, ln x is also gross. That's why it is equal to infinity. With next example, limit formula of this IMPORER integral. Example 3. Negative infinity to positive infinity, 1 divided by 1 plus x squared dx. And we replace infinity with t, and this integral takes the scenario of minus limit t approaches infinity, integral minus t to plus type t, and 1 divided by 1 plus x squared, definition of x. And we should evaluate this integral. 1 divided by 1 plus x squared is antiderivative of arctangent. And limit t approaches plus infinity, it's arctangent, and limits minus t and plus t, arctangent. Okay, arctangent x if arctangent t t also infinity, arctangent if arctangent is bounded minus p divided by 2 and plus p half. Arctangent is between this minus p divided by 2 and plus p half. That's why the graphs of arctangent is look like this. That's why arctangent plus infinity is equal to arctangent minus t. Arctangent limits of arctangent. Limits of arctangent if t is plus infinity, it's equal to p divided by 2, and this is minus arctangent t, but argument is minus also. That's why it is minus p divided by 2. The result is we can take p. This limit is finite. This integral also called convergent, and this limit exists or it is equal to minus infinity. It is divergent, and we can see IMPORER integrals also divided by two groups: divergent integrals, convergent integrals, and divergent integrals in two groups. It's depends this value of these limits. If this limit exists, it is convergent. If this limit doesn't exist or it's equal to infinity, it is also called divergent integral.